Um, okay, hello everyone. Welcome to day two of the Deep Reinforcement Learning Workshop. The theme today is exploration, one of the core challenges of reinforcement learning. Yesterday, we will have four talks, each of 30 minutes, followed by a discussion session. Without further ado, let's welcome today's first speaker, Ian Osman from DeepMind.
Okay, thanks a lot, Li Hong, and hi everyone. One of my first times doing this sort of e-conference, so fingers crossed everything goes okay. But I'm here to talk to you about a paper called the Behavior Suite for Reinforcement Learning. And I guess it's work with a bunch of really great co-authors, as you see there. And a really relevant link is github.com, deepmind/bsuite. Is everything going okay technically, by the way?
Yes. No, we cannot see your screen. At least I cannot.
Okay, that's good. My screen, okay, it says it's sharing. Working better?
No, there it is, yes.
Okay, cool. Well, that's the important thing. Bunch of amazing co-authors and a GitHub link. Okay. And so I guess this talk, it's not just about exploration. It's about all the things that we want in reinforcement learning. So we want to understand our agent behavior and develop better algorithms. I'll post it, yeah, for sure. But if you search bSuite, you'll be able to find it pretty easily. So that means performance, safety, exploration, obviously understanding, everything we want to know about our agents, but we want to be able to make them better. And I guess in the field, particularly in deep reinforcement learning, I guess we sometimes are one field with maybe two camps. And I guess on the one side, particularly in exploration, are the people, you're worried about polynomial time, upper confidence bound, efficient learning. And then I guess on the other side is the sort of more of the deep learning, deep RL side, population-based training, distributed architectures, learning rate, tuning. And the outputs have been historically, obviously they're linked, but they can be kind of different. And even if you're the, one person, such as myself, you might, put on a different hat when you're in different modes. And so on the one hand is sort of an output with, a stylized version of a problem. You say you want to understand exploration really well. And so you look at a simplified setting, something like tabular MDPs, and you understand that problem really well. And although it's not exactly the problem you wanted to solve, but you get some insight into the fundamental scaling of the problems that you hope will carry over. But it's a simplified setting. Now, the flip side of this is maybe something like, AlphaStar, you're trying to take on the world champion at StarCraft. Well, that's clearly not a tabular. You're going to have to pull in all the tips and tricks from deep learning that aren't necessarily amenable to analysis. But, you maybe have a much more impressive and, path to AGI, seems clearer. But on the flip side, maybe, you either beat the world champion or you don't get the same insight and, hey, well, how much longer would I have had to run the computer if the world champion had been, twice as good? Or if the maps had been 3 times as large, would I have needed 9 times as much compute? You don't really get that sort of insight. And, but on the flip side, maybe you're developing, new interesting, tips and tricks and, new algorithms that are really going to push you to AGI. And so I guess bSuite, the behavior suite, which is what I'm going to talk to today, is meant to provide some kind of bridge between these two camps. And by that, I mean simple diagnostic experiments that are designed to provide some amount of understanding, diagnostic tests into the scalability of your algorithm. For example, your abilities in exploration, but are also suitable for large scale, deep RL agents. And so I'll go through this, but that's what the talk is about today. So bSuite is the behavior suite for reinforcement learning, referring both to a paper, we had at ICLR this year, and also the GitHub, okay? And those things go together, right? The paper is really a position paper about why something like this is useful, and the GitHub is maybe the most useful output that you'll be using in your work. And we've had pretty good uptake so far. At one stage we were even trending on GitHub, but hopefully after today's talk, there'll be at least 20 more people or something like that who are desperate to try it. So what's the talk? Well, the most important thing I want to explain is what is bSuite, what type of experiments go into bSuite, why are they useful, and how can you use it going forward? So what is B-Suite? B-Suite is a set of targeted experiments. So the idea is that we're going to collect the best experiments for testing specific aspects of agent behavior. So for exploration, we might build up some specific chain grid worlds of size, small, getting larger, and the agent may pass the small ones, does well, solves it, and then fails. And then we keep, and it always fails. And with that, we say, oh, well, it solved the two smallest grids, so it gets a score, 0.2, okay? And similarly, we might test its memory. We might say, oh, look, you're going to do a T-maze. You're going to start with a really small problem, and we'll grow it and grow it and grow it. And this solved all of them. And then, okay, that gets a score of 1. So this is the kind of way you use it. Now, it should be kind of obvious that, well, what are in these chain grid worlds? What are in these T-mazes? That's the value. Well, and also this score might be slightly arbitrary. But the point is that it's going to be standardized, and you're going to be easily able to compare your notions of exploration and memory against others and run different agents in the same way. So what does that I mean? I think you'll see a lot of test suites which are just the environment. Well, B-Suite is really not just, I'll run through specific things, but the point is that with one flag, you're going to specify the experiment, and that's going to be all of the environments that you're going to run. So, you have to make some choices about what size are the grids and the T-maze. And by I say you, I mean the designers of B-Suite. So let's say that's me. We decided, hey, you're going to run on the chain from size 1 to 100, okay? And that is the B-Suite sweep, right? Now you might come in another time and say, oh, well, we should change that, and we can do it. But the point is, there's a defined only one way to run it, okay? And once you do that, the environment is going to handle all of the logging, everything else is handled, and basically you'll get automatic analysis from that. You'll get a kind of, we're aiming for insight into the scalability of our algorithm. Now I will go through a specific example later that'll make this make more sense. What's the idea? The idea is that if we can bring together all of the highest quality diagnostic experiments that can be simple, so that they're going to strip away confounding factors. We know that exploration is important for doing better in StarCraft, but we don't want to run on StarCraft because there's so many other complicated things in that. So we want something that ideally is just testing exploration, but it can also be challenging. We really want to make it push the agent beyond its normal range, because we want to get insight into the scalability of the algorithm. So we don't just want to say, hey, I've got this great exploration algorithm. It can solve, chain grid world size 100. Well, we want to get some insight of the kind that you might traditionally try and get with a theorem, but we're going to try and get it experimentally by measuring the different sizes and how long did it take to learn. We'll get an insight into the sample complexity of the algorithm. And hopefully we'll make this really fast so that we can iterate this, with not too much compute, get the results really fast. So in terms of software, it's really easy to use. You can integrate it really easily with your code, and the analysis is sort of pre-packaged. So github.com/dmind/bsuite. So there are some tutorials there that are really great, and you can run through it without even installing anything. So I'll skip through this, that's better in the tutorials, but the point is that, okay, you can use it with literally 10 lines of code. And what is B-Suite? It's not just the environment, it's all the logging, it's the analysis, and all the launch scripts. So it's all packaged together. So it should be really easy for anyone to run their agent on B-Suite. So already at the halfway through point in the talk, I just want to highlight, there's, at the moment, we maybe have hundreds of experiments at B-Suite, but I'll just run through 2. So an experiment is the environment that you're going to interact with. So that's the question that Heike asked was, which sizes? Well, it defines all of that. It tells you the interaction, so how many frames, how many episodes you're going to run that, and the analysis, the way that you score it. There's no like roll your own stuff. It's all going to happen automatically. And so an example of this is, okay, we want to test memory. So you might ask, okay, well, how long can an agent memorize? We have a T-maze, you wait n steps, and you get the answer right or no. And it's just, very concrete. And, there's a scoring function here is the percentage of which you get less regret than 75% of random. And so the idea is like, memory is a complex, we could have an epistemic discussion of what the meaning of memory is, but rather the B-suite approach is that we're going to instantiate a simple problem that somehow represents one of the key challenges of memory, and we'll just be able to measure the agent performance really dispassionately, really objectively on this task. Okay. So here are examples of running an actor-critic RNN, bootstrap DQN, and DQN on it. And these are the plots that would come out automatically from running it. And you can see, okay, you know, in terms of score, the RNN one did kind of well and the other ones did terribly, right? But score between 0 and 1. And yeah, that's cool. I guess that's what you'd expect the RNN to have, you know, some notion of memory that DQN or bootstrap DQN do not. But where this stuff becomes more interesting is maybe looking at the scaling plots, okay? And so this is looking at the percentage of correct, actually it's the percentage of incorrect episodes after 1,000 episodes. So this is mislabeled, it should be the incorrect. Are they not visible? I hope they're visible, jeez. Okay, and so you're looking at length 1 to 100, and we can see here that, you know, basically the actor-critic RNN does really well on everything up to size 30 and then completely fails, okay? Whereas DQN and bootstrap DQN just completely fail any stage after 1. And so what this is doing, right, it's hopefully giving you some insight into the scaling of this algorithm, because I haven't told you anything about this actor-critic RNN, but actually this was run with a backprop through time window of 30 steps, right? But you could kind of guess that from the way that this works. It works perfectly, and then abruptly stops working. So we probably wouldn't have expected it to keep working, you know, if we ran it twice as long on size 31. It doesn't have, or size 40. It doesn't have that sort of characteristic. So you get some insight potentially into the scaling, even beyond, you know, what you know a priori. And I guess similarly, you know, this is we're in a session about exploration, so maybe some of you will have encountered the deep sea environment, but I guess it's a stylized kind of tabular MDP that's meant to be like a needle in a haystack. And so you're in an n by n grid. You always start at the top left where the boat is, and you're going to fall 1 row per time step. You take action 0 or 1 to go left or right, left or right, left or right. You have a small cost when you go right, but a large reward if you make it to the bottom right, where the treasure is. So basically, almost all the policies you ever take will have, you know, either 0 or negative. But if you make to this one policy, which is right, which is, you know, an arbitrary string of 0s and 1s, then you get a big reward. This is a needle in a haystack problem. And if you don't do efficient exploration, deep exploration, you'll take 2 to the n episodes to find this treasure, right? But if you do deep exploration, it's possible to learn much faster, okay? And so for this B-suite, you know, you run on sizes 10 to 50 for 10,000 episodes, and your score is those where you do better than this 2 to the n baseline, okay? And so this is the idea that, hey, you know, it's difficult to put a handle, you know, to say exactly what exploration means. You know, when in some senses you could have a definition in terms of polynomial regret or faster learning. But if we can instantiate, you know, those type of polynomial regret bounds might be hard to come by for something like DQN or, you know, bootstrap DQN or, you know, a pseudo count method. But at least you can always run those deep RL methods on DeepSea, and you can just see how they do, right? You can empirically investigate the scaling, even if you can't prove it. And so, you know, this is running actor-critic RNN, bootstrap DQN, and DQN. Bootstrap DQN, I guess, is a variant which is claiming that it does better exploration than DQN. And at least on this particular notion of exploration, it seems like it does better. But again, the interesting thing is not in the scoring, but it's in the, you know, the scaling plots. And this is looking at the number of episodes it takes until you have some average regret less than 0.9 per time step per episode. Okay, and you can see that on this dashed line is 2 to the n. You know, all of this is explained if you go in through the GitHub or through the analysis material. But basically here we see, look, this is the 2 to the n we'd expect of a, you know, an inefficient scheme. And you can see none of these DQN, actor-critic RNN, they don't do better than that. And bootstrap DQN, it's clearly doing much better than 2 to the n, right? And also, even though we've run this plot, you know, we've run these experiments from size 10 to size 50. If I had to ask you, hey, I got to run Bootstrap DQN on DeepC of size 60, let's say. Well, I guess the hope is that by doing an experiment like this, you might feel more confident in saying, hey, you know, I actually think it probably would solve it. And maybe it would take around, you know, 3,000 episodes, something like that. Because this, unlike the one we had before, this looks like a smooth curve, like a smooth polynomial scaling, right? And so, although, you know, this is far from a proof, but we hope that, you know, by collecting these indicative examples, you can get insight into maybe complex algorithms that are difficult to analyze, you know, which can feed both the theory and the practice, you know, by cross-pollinating ideas. So I guess I've already started on this. So it's really, why are these experiments useful? I guess the idea is that, you know, if we really could only stick to algorithms for which we had, you know, provable guarantees, well, for one thing, I don't think we would have been using deep learning, right, for a long time, and we may not even be using it now. So practical algorithms often are ahead of the theory. I guess this can be something like an MNIST. We can, for reinforcement learning, we can try to collate, you know, simple, informative experiments that can help with algorithm design. I guess, you know, I don't have time to go through all the code, but it's open source, allows for reproducible research, easy comparisons across code bases. You know, we have examples running it with OpenAI baselines which we open source, Dopamine. You know, this is kind of platform agnostic. I guess another big thing is that through this effort of collecting B-Suite experiments, we can try and instantiate the key issues. You know, a lot of people, for example, we all kind of know, oh, we feel like hierarchical RL is important. But at the moment, I don't think we have a clear and simple experiment, which would be like, oh, if you did really good hierarchical RL, then you should be expected to do well on this task, right? And so maybe even just encouraging people to look for those kind of examples will help us to find a new clarity in our research. And I guess they can be, you know, unit tests for core RL concepts. But I won't go through this. You know, this is, I guess, how you load the results. It's pretty, I guess, this is now technical stuff. We don't have time to go through it. But I guess if you click through that link, bit.ly B-Suite Colab, you can see that it kind of handles this all automatically for you. No time for the interactive session either, but, you know, it's just a lot of example code and output, which you can all find through the GitHub. Yeah, I'll talk about, I guess, you know, MNIST, you know, I guess to count, I'll just talk, yeah, it's a good question actually. So Alec is sort of saying MNIST is at least representative of a real world problem. And I guess we don't know, you know, we don't know if these are representative of real world problems, but I guess the idea or the effort is to, and part of it, you know, I guess you have to argue it through the paper and kind of, you know, from first principles is to kind of claim that is to first, you know, I guess I would claim, let's take the memory, the T-maze. Well, then I'll say, okay, the T-maze is in some sense representative of some notion of memory. Now, sure, it's not exhaustive, but I think most people would agree, hey, you know, I can cite various works in psychology or other RL. And same with DeepC, you know, I can kind of make a case for it. Now, if you say to me, oh, you know, T-maze is completely, it has nothing to do with memory, that's complete, you know, rubbishy, and I don't want it in there. Well, I think the approach that we're taking is that we'll allow more environments. So maybe I think you'd have a hard time convincing me, hey, we shouldn't have T-maze in there. But if you say, hey, look, I've got a much better experiment for testing memory, well, then, you know, with compute, you know, that we have, or the deep RL approach, we'll add that into the suite. And I guess we can be data-based about that.
Ian?
Yeah.
Yeah. So we have about 2 to 3 minutes to go.
Okay, I'm out of time. So the other last thing is, you know, if you run it, you also get an automated LaTeX appendix, you know, so you can add it to your, you know, I've done this. If you have an agent, you might as well run it through B-Suite, get these kind of output for free. We want better experiments, you know, I guess I already started with that with Alec. We have some people on a committee who are going to help curate this. But yeah, let's talk. Hopefully this is interesting to you. Maybe some of you had a look at it before, and looking forward to questions. Thank you.
Yeah, thanks, Aaron. This is really interesting. Now we have about 10 minutes for questions from the audience.
Hi, Ian. So I think I actually might have brought this issue up whenever the B Suite first came out, and we had a little Twitter discussion about it. But I'd kind of just like to follow up on it a bit. So first of all, I think B Suite's great. We've used it in my group some to analyze some of the work we've been doing. Um, but I want to get your thoughts on the trade-off between that you kind of mentioned at the beginning again of like simplicity and understandability versus these more complex things. And a lot of these tasks they really don't seem to be representative of real tasks. And I just want to get your feeling on how important that is. Like, do you know do we think these simple domains actually, unfortunately, function fundamentally differently than complex ones because, for example, of how important representation discovery is in a lot of these problems like exploration, etc. And without much structure to bite onto, some of these problems just kind of reduce to something combinatorially hard that we wouldn't expect any algorithm to do well on unless it was designed with like an inductive bias to sort of do well on that type of problem, which then doesn't really tell us anything interesting in the end.
Yeah, thanks a lot. So I actually think that's a really good question, and a piece of work which kind of we had in the works, but kind of got thrown off from COVID was an analysis of this. I guess an analysis of what correlates between B Suite and other, let's say, problems you care about. Now if I'm going to throw this back to you, I say, well, what are the problems that you care about? And the answer is probably not Atari, right? And it's probably not, MuJoCo, right? So I think that it's kind of, that you can ask the same question about those things. Like, well, do I think Atari corresponds to the problems that I really care about? And if you're pointing out that what we have in B Suite at the moment has huge amounts of, missing pieces on the task.agi, definitely, 100% it does. But I actually think that maybe even if that is the conclusion, even if that turns out to be true, you might still find this useful as like a debugging or like testing thing, because you may just be like, okay, well, look, I know that some of the problems in there are to solve MNIST, as a bandit, or to solve mountain car. We should obviously be able to solve that, right? And then I think that if we can, if it turns out that some of the problems of RL and representation learning are just irreducible, right? Because it becomes really hard when you have to do exploration with representation, with generalization, with memory, right? Which I do agree, that's obviously harder. But if it's irreducible, cool, it's irreducible. Like there was nothing you could have done. But maybe in the effort of trying to distill these things into smaller pieces, maybe you'll find smaller bits which we can make better progress on, or we can understand better what exactly it is that makes those problems so difficult.
Yeah.
An example being HRL. Let me tell you this way. I think like HRL, it's hard to tell whether, how could you claim to make a significant breakthrough in HRL? I think it's difficult to say when you've done that versus just RL. It's not even clear at the moment.
Yeah, that's a good point. I mean, do you think there are ways, like, or do you see a path toward creating domains like these, but just with like that little extra special thing added so that there is enough structure in the problem that you can do interesting representation learning, for example, and see how it interacts with all these other pieces that you're trying to study?
Yeah, I'll say yes, but on the other hand, I guess it's obviously not easy because I don't think we have a good example of that. And if I'd have been able to come up with one, I would have added it. But the approach we want to say is like, oh, we want this to be a place where we can, it's obviously difficult to do it, but we want to be able to consolidate. And if you come up with a great example, well, we want to include it. I think the only trade-off we have is some of the computing time stuff. And so we want to keep it, we have consciously decided to target maybe just this small, lower compute regime.
But Ian, one thing you could certainly do is to, like if you think about something like DeepC, instead of just keeping it tabular, it's pretty easy to add some kind of underlying emission process for more complex.
Totally. So actually, I even have coded up a version of DeepC where your row and your column was MNIST digits, right? So if someone wants that, we can do it. I just thought it was, it could become a bit confusing. And also I don't want this to become like the Ian, it already is a little bit, I guess I'm presenting it, but I'd rather, if you are interested in that, cool, we'll add it in. But I'd prefer it actually to come from you, Alec, because then you'd be like, oh yeah, you'll definitely run on it.
Well, I mean, we are definitely playing around with such experiments anyways. So yeah.
Yeah, so I guess that's another value proposition is, I guess, if you're already playing around with the thing, if you feel like you can really, put that final layer of polish of like, oh, look, in particular in looking at scalability or stuff, well, then it's great for you to add your experiment, and I'll help or whatever, you add your experiment to B Suite, because you'll automatically get all the other ones kind of for free, plumbed in. And then anyone else who comes and writes a paper, you won't have to tell them, hey, why didn't you run it on this thing, right? Because they'll run it more easily on yours. And they'll also, how frustrating is it if they try to re-implement it, it's difficult, right? And you make a small mistake and suddenly it's not the same thing as what you wanted it to be. You can be like, oh, look, no, run from this, it'll be the right thing.
Can I ask you a question?
Yeah. I don't know if I picked.
Having code available for different environments and thinking about how can we share code, I think is really important. And we sort of have these frameworks from multiple groups at different times, and sometimes the frameworks just don't stick. So I kind of want to know what's different about B Suite. Now here you say we want better experiments. What would be like the ideal outcome? Like if B Suite would make us do experiments that are like the following.
Okay, yeah, that's a really great question. So I think there are a few things that are different. So the first is, because we made it behavior suite, so we only look at things that the agent does, that we've made it easier to integrate it with other, let's say, frameworks, because basically all you do is you swap in the environment. Now that at the moment we support that as either DMM or OpenAI Gym environment. And then if you just run your agent on this environment, that's it. That's all you need to do, because basically the environment is automatically doing all of its logging. It's counting all of your frames and stuff like that, because, and then because it's kind of behind the curtain of the environment. So then you didn't need to count and add up this and add up that and whatever. So we have examples of running it with, let's say, Dopamine, OpenAI baselines, et cetera, and a few other things internally in Google. So we kind of hope that, okay, it's obviously not simple, but I want it to be like, oh, you can just put this environment in your framework and then it's just going to work. So that's the idea. What do I think? I think that it makes, the other question was about how does this make your experiments better? I think it makes them better just because, normally you have to write this loop of maybe handling the data, adding up the rewards, subtracting the noise, I don't know, like processing it. And this is kind of coming batteries included. So I think that makes these things a bit easier. And I guess what's my ideal outcome for this? My ideal outcome is that, we'll collect the best experiments for this, you're going to need other experiments for sure, but of this genre of simple diagnostic, insight driven experiments, we'll collect all the best ones. And probably we'll collect a few extra as well that weren't as good as the others, but they seemed like a good idea. But we'll collect the best ones, you'll collect yours. And then whenever you write a paper, whenever you write an agent, you'll always just be like, oh, I'll run it on B Suite. Now, to give you an example, when I say it doesn't cost a lot to run it, we also included GCP instructions, Google Cloud Compute. But I think with Amazon and whatever, it's the same, pretty easy. And the last time I looked, the cost of running a full sweep was about $4 or $5. Okay. Now, so it's not a lot. It takes like $4 or $5, takes about half an hour. So compared to some of the things, I think it's reasonable for you, maybe if you're reviewing, you're like, oh my God, you might say, hey, why didn't they run on Windy World or some type of world that you like? But rather than saying that, just say add Windy World to B Suite or, whatever problem you want. And you say, hey, why don't you run it on B Suite? And then at least you can always get this comparison. That'd be great.
Okay, so maybe you can reserve the last question for the attendees. There's a question, could metrics be combined for trade-offs similar to precision and recall are combined for F1 to account for complexity in problems. Maybe we can find experiments that are in between exploration and generalization, for example.
Yeah. Well, I think that that is part of the, what we have. Could it be done? I think probably yes. Has it been done? Absolutely, definitely not. I think that kind of thinking, though, will help us to have more effective discussions on all of these topics in RL, because I think that there are probably things, spokes on this wheel that we don't even know yet that are a problem, or this turns out that scale is not such a big problem. It's probably credit assignment is the same as generalization, but at least if you encourage this sort of encourage to measure the things we can measure, and then otherwise start trying to find ways to measure things that we don't understand that well, I think it'll help anchor conversations on some of these theoretical, and probably in the future, probably will move beyond some of these diagnostic experiments, because you can have a true theory of, exploration in deep RL. But maybe these kind of, kind of like psychology experiments, you might view it, are a path that brings us to that level of understanding in the future.
Nice. Okay, yeah, thanks a lot. Thanks, Ian. So now we can, let's